Hello students, in this video we'll see the solution to the back exercise of chapter 10 Gravitation. So I'll read the first question. You have to listen to the question carefully. How does the force of gravitation between two objects change when the distance between them is reduced to half? Okay. How does the force of gravitation between two objects change when the distance between them is reduced to half? So let us consider first two objects and let m1, m2 be their masses. So here let m1 and m2 be the masses of two objects and let r, small r, be the distance between them. And F, capital F, be force of gravitation between them. We know that according to Newton's universal law of gravitation, this F is equal to capital G m1 m2 over r square. Now, what is the question? How this force would change when the distance between them is reduced to half? So, let us take the distance is reduced to half. If the distance between them is reduced to half, let us say now distance is r dash. It is equal to half of this distance. R dash is r by 2. Then let us see how does the force of gravitation change. Let the force of gravitation be represented by F dash now. According to the Newton's universal law of gravitation, F dash will be capital G m1 m2 over r dash square. You know this force is proportional to the product of the masses of two bodies and inversely proportional to square of the distance between them. Now distance between the two objects is reduced to r dash. Okay, and in the next step I have substituted for r dash, which is r by 2. Remember, it is r by 2 whole square, and when you open the bracket it becomes r square by 4. And it is G m1 m2 divided by r square by 4. It means G m1 m2 over r square into 4, or G m1 m2 into 4 by r square. So you can write it like this. F dash is equal to 4 into G m1 m2 over r square. But see there, you can number this as one equation. From 1 we can write G m1 m2 over r square is capital F. So we can write F dash is equal to 4F. It means when the distance between the two bodies is reduced to half, gravitational force between them becomes 4 times the original gravitational force between them. I hope the numerical is clear to you. Now the second question. Gravitational force acts on all objects in proportion to their masses. Why then a heavy object does not fall faster than a light object? Listen to the question carefully. Gravitational force acts on all objects in proportion to their masses. We know that according to Newton's universal law of gravitation, the gravitational force between two bodies is directly proportional to the product of their masses. Why then a heavy object does not fall faster than a light object? Now in the second sentence, we come to know that they are talking about freely falling bodies. They are saying, why then a heavy object does not fall faster than a light object? This we have considered when we were doing the theory part of the chapter, that when you throw two objects from certain height, irrespective of their mass, they fall with the same acceleration. It means a stone or a rubber ball of the same size, they will fall from the same height. If we drop them or throw them with same velocity, they are going to reach earth at the same time. They are going to travel the same distance in same time. Okay, so let us see how we are going to write it. Now you can look at the board. We have taken, let mh be mass of heavy object, ml, small ml be mass of light object, capital FH be force of gravity on heavy object. Why I have taken force of gravity? Because in the second part it is given that Why then a heavy object does not fall faster than a light object? This we know that free fall motion is caused by force of gravity only. So Fh is force of gravity acting on heavy object, and let Fl be force of gravity on light object. We know that according to Newton's second law of motion, we can write Fh is equal to mh into g, and Fl is equal to ml into g. We know that this g, we have seen the g variations, and we know that normally we assume Earth to be a perfect sphere, and so we consider small g is constant on or near the surface of Earth. So as acceleration due to gravity, what is acceleration due to gravity? Acceleration which is produced in a freely falling body. We know that this acceleration due to gravity on Earth's surface or even close to the surface of Earth is given by this formula, small g is equal to capital G m over r square. And we know it is constant for all bodies irrespective of their masses. As you can see in the formula, small g is equal to capital G capital M divided by r square. So in the formula of g we don't have mh or ml. It depends upon mass of the Earth and radius of Earth. So, a heavy object does not fall faster than a lighter object. So, I think so the question is clear to you. But at the bottom in the brackets, I have given explanation which you don't need to write in your answer. But it is for your understanding. What I have done, I have taken GH. Let us assume that the acceleration due to gravity is different for both the bodies. Now from the equation Fh is equal to mh into gh, if I write, gh will be Fh upon mh. Now put the value of mh from Newton's universal law of gravitation, that is capital G capital M into small mh divided by capital R square. So this is Fh divided by small mh. We know when we do the simplification, small mh will get cancelled and we are left with gh is capital G capital M divided by r square. And similarly, if I take acceleration due to gravity on the lighter object to be gl, and if I proceed in the same manner, then again I can see that gl will be equal to fl upon ml, and the final answer will be capital G capital M over r square. So from here we conclude that small gh is equal to small gl. It means acceleration due to gravity on heavy object or light object, it remains the same. So two bodies, even if their masses are different, they are going to fall. No heavy body is going to fall faster. Okay. So here we have got the explanation for the answer why a heavy object does not fall faster than a lighter object. Basically, in short, acceleration due to gravity for the two bodies is same irrespective of their masses. Now the third question is, what is the magnitude of the gravitational force between the Earth and a 1 kg object on its surface? In the bracket it is given, mass of the Earth is 6 into 10 raised to 24 kg and radius of the Earth is 6.4 into 10 raised to 6 kg. Sorry, 10 raised to 6 meters. Okay. Now I'll read it again. What is the magnitude of the gravitational force between Earth and a 1 kg object on its surface? Given mass of the Earth is this. So given mass of the Earth, we represent it by capital M usually. So we'll write capital M is equal to 6 into 10 raised to 24 kg. Okay. Radius of the Earth is given as, capital R is given as 6.4 into 10 raised to 6 meters. What is the mass of the other object? 1 kg object they have given. So small m, mass of the other body is 1 kg. You have to find the gravitational force between the Earth and the object. So capital F, let it be capital F, and this we have to find out. Now first see if any conversion is required as we usually do. kg meters. Everything is in SI system, so no problem. We know for F, G value, even if it is not given, we know the value. So I have written it here. Capital G is taken as, we can take it as 6.7 into 10 raised to minus 11 Newton meter square per kg square. Now we are going to use Newton's universal law of gravitation for this. If you want, you can mention it here. According to Newton's universal law of gravitation, capital F is equal to capital G, capital M, small m divided by capital R square. So you need to write the formula, there are marks for the formula, and you need to substitute the values as given here. For G already you know, M, capital M, small m divided by R square. Now in this case, what I have done, actually I have not done the calculations. I have not done it manually, I have not used any calculator. Calculators are not allowed in exams also. But at least in this case you know, small m is 1. Capital G, capital M over capital R square. What is this? This is small g. And you know, this small g value on the surface of Earth is 9.8 meter per second square. So this will be, even if when you don't do the calculation, you know that Gm over R square, this answer should be 9.8 into 1, and so it will be 9.8 only. And since it is force, write Newton. So the answer is F is equal to 9.8 newtons. I hope this is clear, quite very simple numerical. Now the fourth question. The Earth and the Moon are attracted to each other by gravitational force. Does the Earth attract the Moon with a force that is greater or smaller or the same as the force with which the Moon attracts the Earth? Why? I'll read it again. The Earth and the Moon are attracted to each other by gravitational force. Does the Earth attract the Moon with a force that is greater or smaller or the same as the force with which the Moon attracts the Earth? Why? Students, we have done Newton's third law of motion, according to which to every action there is always an equal and opposite reaction. It means when any body exerts force on the other body instantly exerts equal and opposite force on the first body. So the two forces, one of which can be called as action and the other can be called as reaction, they have equal magnitudes, only their directions are opposite. So here we have got the answer that the Earth attracts the Moon with a force that is same as the force with which the Moon attracts the Earth. We know they are talking about the magnitude only. Okay? The Earth attracts the Moon because what was the question? If you remember the question, what was the question? They had asked that, does the Earth attract the Moon with a force that is greater or smaller or the same as the force with which the Moon attracts the Earth? So they are talking about the magnitude only. So we know that the Earth attracts the Moon with a force that is same as the force with which the Moon attracts the Earth. We can mention here that the two forces are having equal magnitude, but yes, their directions are opposite. Now, question was also why? Because according to Newton's third law of motion, every action has an equal and opposite reaction. So according to this, the two forces, that is the force by which Earth attracts the Moon and the force with which Moon attracts the Earth, they are having equal magnitudes, although their directions are opposite. I hope today we have done the first four questions we have solved of back exercise, and I hope the solution is clear to all of you. So we'll continue with the back exercise in our next video. Thank you, students.